All right, this is going to be a good one. This one is titled, Is Probability Estimation Possible in Trading? Part 1. As a preliminary, for the purposes of this video, probability estimates in trading are probability estimates about price only. So if price is currently right here, and we were to pick two specific prices on either side of the current price, perhaps one right here, perhaps one right here, what is the probability that this price, this one right here, will be reached before this price, or the other way around? This can be a useful academic question, but it's going to be really useful for traders who might, for example, have a position open with a stop loss and a take profit at certain prices. What is the probability that the take profit will be hit before the stop loss? Now let's talk about the purpose of this video. Most traders don't estimate the probabilities of their trades closing in profit, and this is often because they don't think it's possible. There are several ways this is expressed, but it's common to hear about real or true probabilities being unknowable for individual trades. Perhaps probabilities do play some role in their thinking, but it doesn't really apply on a trade-by-trade basis. Now, for me personally, the way real and true probabilities is brought up is interesting, especially because it seems to imply there's something false, or at the very least, less true about the probabilities that we find through probability estimation. So this video is going to be an attempt to think through this issue. My suspicion is this is not as big of a deal as it might first seem. So to do this, I've contrived a couple scenarios that are intended to highlight different aspects of this issue. And the first scenario is called 25% die. You have found what appears to be a box of weighted dice. According to the packaging, they will land on one side 25% of the time, and the other 5 sides each have a probability of 15%. But the box is damaged, and it's unclear which side is weighted. The damage to the box has left only one die, but it does appear to come from this set. The only way to determine which side is weighted is to test it. The first question I have of this scenario is, what is the probability that the first roll will land on 1? Well, if the die is weighted to roll on 1, the probability distribution would look like this. 25% for one, 15% for the other options. But we aren't sure which side it is weighted to favor. If it's 2, the probability distribution would look like this. If it's 3, this. 4, 5, 6. And if we average out all the probabilities of rolling a 1, we get the same 16.7% we would have for a normal die. From our perspective, given the information we have, every single side of the die has an equal chance of landing. I think this is the most sensible way to look at this situation. But this way of looking at probabilities differs from the true 25 and 15% probability we also know to exist from the box. What this suggests to me is that there are 2 different ways of viewing probability. One is probability inherent in the event itself. This perspective has probability residing in the die, or perhaps in the act of rolling the die. This is the 25 and 15% odds that we know to exist from what we have discerned from the box. In some way, this kind of probability is fixed. Only a change in the event itself changes the probability here. The second is probability based on available information. This perspective places probability in the mind. This kind of probability changes with new information, even if the event itself remains the same. It's possible to think of these as being objective probabilities and subjective probabilities, but the reason I don't want to use this language is because it could suggest the probabilities based on available information are wishy-washy and incorrect. But if done correctly, probabilities based on available information are rigorous. Instead of thinking of them as incorrect, I think it's better to think of them as correct given whatever limitations we're facing. The second question I have for this scenario is, how many times do we need to test the die before we can begin to adjust probabilities? One sensible way to approach this is to figure out the required sample size for developing sufficient confidence to determine which side the die is weighted to favor, and start using the probabilities that we know to exist from what we can discern from the box. But I'm going to be a bit cheeky here and say, what if it's 1? So, we know the probabilities inherent to the event itself differ from the probabilities based on available information. And here I've prepared a table where one column represents the probabilities of the event itself if the die is weighted to roll 6s, and the next column is the probabilities based on available information. And here are the differences. If you add up all the differences, it adds up to 16.7%. And this will also be the total if the die are weighted to roll on any other number. So we know that our probability estimation is off by this amount. We are just unsure what adjustments need to be made to improve it. The wrong adjustments will make it worse, and there are more ways to make wrong adjustments than right ones. From what we can discern from the box, we know that our probability estimate should not go under 15% or over 25% for any individual die face. If we are completely confident that one side of the die is not the side the die is favored to roll, we would attribute that a probability of 15%. Likewise, if we are completely confident one side of the die is the side the die is favored to roll, we would attribute that side a probability of 25%. At present, we are 1/6 certain that each side of the die is the side of the die that the die is favored to roll, and 5/6 certain that it isn't. And so for this reason, we would put this arrow that I'm moving around 1/6 up the spectrum. So about here, I guess. And 1/6 of the way from the spectrum from 15% to 25% is 16.7%. Now here I've done this for every die face. We have 6 candidate die faces, and we think there's an equal chance that any of these die faces are the side the die is favored to roll. Well, when we roll the die, we know there's a 25% chance that it will roll on the side that it's favored to roll. So when our first roll is a 3, we know there's a 25% chance that that's the side the die is weighted to roll. So we are going to want to move the arrow above 3 25% of the way across the spectrum from 15 to 25%. So we'll move this and change this to say 17.5%. So 3 is now our most likely candidate, and the other die faces are less likely, so we're going to have to move those down a little bit. Let's move these down just a little bit, and there. Now each die face is still a really good contender or a really good candidate for the side that we think the die is favored to roll. It's just that this one die roll gives us a very slight bias towards thinking 3 is the best candidate. Let's imagine the die is actually weighted to roll 6s, and we plug these numbers in. The total difference between the probabilities inherent to the event and the probabilities based on available information has gotten worse, growing from 16 and 2/3% to 17%. That's a growth of 0.333%, and there's a 75% chance that this approach points us in the wrong direction. Or, for every step in the right direction, we will take 3 steps in the wrong direction. But with that said, consider what would happen if we rolled the side the die is weighted to roll. So if we rolled 6, instead of the total difference increasing by 0.333%, it goes down by 1.667%. So in this scenario, even though the steps in the right direction are less common, they are the size of 5 steps in the wrong direction. In other words, even though the majority of the time a single die roll will give us slightly worse probability estimates, on average, it improves them. Now, let's look at what 3 steps in the wrong direction and 1 step in the right direction actually looks like, though. If we did this process 4 times and got 4 different numbers, and only one of them was the side the die is favored to roll most, we would have 4 better candidates for which side the die is favored to roll, and 2 sides that are less likely, though certainly not impossible. Because of the small amount of data available, we are only able to take small steps from our starting assumption of 16.67% for each die side, and our cumulative accuracy only improves from 16.67% to 16.15%. Nevertheless, these small steps, often in the wrong direction, are improving our probability estimation. In this scenario, at least, we are able to begin to bridge the gap between probabilities inherent to the events themselves and the probabilities based on available information very early. Even if probability estimates are not perfect, they are improving, and that's meaningful. So here are what I think the major takeaways are for thinking through scenario 1. First, we can distinguish between probabilities inherent to events themselves and probabilities based on available information. Second, we don't have to directly know the probabilities inherent to events for us to be able to improve our probability estimation. Working on our probabilities based on available information is sufficient to give us some kind of advantage. So I think this scenario is productive to think through, but it's not often in the real world that we would have the advantage of having the numeric values of probabilities while missing which outcomes they're associated with. So let's move on to scenario 2, an unknown percent die. Again, you have found what appears to be a box of weighted dice. But at some point, a mouse made the box its home, and the part of the package that tells you how often you would roll 6 is damaged. It's beyond the scope of this presentation to try to estimate the probability of this happening. Anyway, the mouse has only left 1 die undamaged, but it does come from this set. So the first question I have for this scenario is, how do we bridge the gap between probabilities inherent to the event and probabilities based on available information here? The quick answer would be to build a large sample size and use the percent of times it rolls 6 as a probability based on available information. And I think this is sensible and basically correct. But I think to understand how this works better, we should start by looking at what we can do with a single die roll. In the first scenario, we were looking at different die sides as candidates. After rolling the die 4 times, we had 4 sides that we thought each had around a 19% chance of being the side the die was weighted to roll. And because of that, we would place arrows 19% up on this spectrum from 15 to 25%. We can make a similar diagram where the die faces are replaced with the probability of rolling a 6. Of course, if we are treating these probabilities as candidates, even if we are only considering integers, we have 101 candidates, which I'm not going to draw that. But what I have here is 0%, 1%, 2%, and then some zigzag representing, I guess, everything in between 2% and 49%, 49, 50, 51, another zigzag to represent another gap, 98, 99, 100. And for now, this will suffice. Each spectrum goes from 0% to 100% here, so being placed halfway means that we think there's a 50% chance that this candidate is the correct percent chance of rolling a 6. Here we're going to make the starting assumption that each of the 101 candidates of integers between 0% and 100% have an equal likelihood of being the number that the mouse chewed through. Basically, we're going to start completely unbiased. But if we roll a 6 on the first roll, 0 gets ruled out as a possibility. So we'd move this down. And while it's not an impossibility, it's not a very likely outcome if the die only had a 1% chance of rolling a 6. So we move this one down too, but not as much. And same to a lesser extent for 2%. For the middle numbers, 50% wouldn't change at all, but 49% would go down very slightly, and 51% would increase very slightly. Here we go. And numbers like 98%, 99%, and 100% would increase the most. And it would be just like this. Collectively, these 101 candidates would still add up to a total of 100%. If I were depicting all 101 candidates here, it would be clear that these blue arrows are forming a straight line of their own, very slowly climbing from the 0% on the 0% probability of rolling a 6 to 1.98% on the 100% probability of rolling a 6. Something I want to point out, though, before depicting these probabilities with this kind of line, is that when we depict the likelihood of these candidates with arrows on a spectrum, is that individually, none of these candidates are particularly likely. The arrows are all towards the bottom of the spectrum. But I guess this isn't surprising with a sample size of exactly 1. Alright, so we have a bunch of candidates for the chance of rolling a 6. How do we turn that into a probability based on available information of rolling a 6? In scenario 1, we looked at die faces as candidates, and based our probability estimates on the chances of each candidate being correct. After 4 die rolls, we had 4 better candidates and 2 lesser ones, so we really had no idea which specific die face was the 25% side at all. Nevertheless, this process still allowed our probability estimates to improve. We want to do the same thing here. Ideally, we don't simply want to pick the best candidate. We want our probability estimate to incorporate the chances that any candidate happens to be correct. I think this is simplest to see when we have no die rolls at all. If we are completely unbiased about which candidate is most likely to be correct, there is no best candidate to pick. The line of blue arrows is completely flat. But some probability estimates will be better than others. Say we were to make our probability estimate 100%. What if the die is weighted to roll 6 50% of the time, or 0% of the time? Well, if the die is weighted to roll 6 100% of the time, then our probability estimate is correct, and there is no difference between our probability estimate and the probability inherent to the event itself. But if the die is weighted to roll 6 50% of the time, our probability estimate will be off by 50. And if the die is never supposed to roll a 6, the probability estimate will be off by 100. So our probability estimate will be completely wrong. So if we consider the possibility of each of the 101 candidates being correct, the difference between our probability estimate of 100% and the chance of rolling a 6 represented by each candidate will average out to 50.5%. Let's compare that, though, to if our probability was 50%. If the die is weighted to roll 6 50% of the time, then there is no difference between our probability estimate and the probabilities inherent to the event. But if it's 0%, it is off by 50, just as it would be if it were 100%. So the most wrong we can be is half of what it was when our probability estimate was 100%. And our average difference for the 101 candidates is now just 25.5%, more or less half of what it was when our probability estimate was 100%. The probability estimate of 50% is much better than the probability estimate of 100% because it is less likely to be severely wrong. Now let's consider that first die roll. If we roll a 6, the line of blue arrows slopes very gently upwards. So our single best candidate is 100%. But the difference for candidates around 100% matters much more than it did before, while the difference for the 0% candidate doesn't matter at all. So we need to weigh the difference for each candidate appropriately. So this is what the orange line here does. It lets us know how much the difference between our estimated probability and any particular candidate probability actually matters. And we want the average of this value to be as low as possible. We can see that the difference between our probability estimate and the 0% candidate is high. But it doesn't matter at all. Meanwhile, the difference between the 100% probability estimate and the 90% candidate is not nearly as big, but because of the relative importance of the candidate, it matters more. And on average, for the 101 candidates, the average of the orange line is 33.3%. But what if our probability estimate was 50%? So now our orange weighted difference line has this more interesting shape, but it has the same average value as the original red line of 25.5%. And that is still lower than the average value of the orange line when our probability estimate was 100%. So even though 100% is still our best individual candidate, 50% remains a better probability estimate given the available data. But did the new data change anything then? Well, yes. We can lower our average weighted difference for the 101 candidates to 18.2% by making our probability estimate 71%. Given the number of candidates we have that are nearly as credible as our best candidate, a probability estimate of 71% is more appropriate than a probability estimate of 100%. As our sample size increases, the best individual candidate gets more credible, while most candidates start to get ruled out as realistic possibilities. This will lead to the optimal probability estimate quickly getting closer and closer to the best individual candidate, which is going to match the percentage of times a 6 is rolled. The average value for the orange line, the weighted difference, will also fall. So here we have 1 6 in 3 rolls, making 6s 33.3% of die rolls. And with a probability estimate of 39%, our average weighted difference falls to 16.7%. Here we have 2 6s in 10 rolls, making 6s 20% of die rolls. And with a probability estimate of 24%, our average weighted difference is now only 9.7%. And here we have 13 6s between 50 rolls. And we can start to see a clear bell curve form on the blue line. We have been able to rule out the majority of candidates as realistic possibilities we need to worry about. With the weighted difference of the candidates lower than around 8% and above around 52% or so being so low, it can't really be seen on the graph at this scale. The average weighted difference for the 101 candidates is now only 4.9%. Our probability estimates very nearly match the percent of times we rolled a 6. Using that percentage as our probability estimate would be fine at this point. And this is what it looks like with 126s in 400 die rolls. We can really see what the increased sample size is doing for us here. We have ruled out most candidates as being realistic possibilities, narrowing the blue bell curve to a few credible contenders. The orange line for the weighted difference when making a probability estimate of 30% now only averages 1.8% between the 101 candidates. Even more than before, we can basically just use the percentage of times we roll a 6 as our probability estimate. But okay then, if we can just use the percentage of times we roll a 6, why bother explaining any of this? Well, I think people often look at confidence intervals and margins of errors with the idea that we are looking for one true number within a small range of possibilities. And we should absolutely be narrowing down our candidates. But probability estimation doesn't require there be one single definite answer. Having probabilities attached to each possibility is sufficient for probability estimation to be meaningful. In fact, I'd say that's the essence of probability estimation. It's just that building a large sample size allows the occurrence rate of a specific outcome, like rolling a 6, to adequately stand in as representation for the full range of possibilities. Okay, let's move on to my second question for this scenario. What exactly is the box doing for us here? I mean, basically any 6-sided die would have a chance of rolling a 6. So what new information is the box really giving us? And what does this allow us to do? So let's consider if we don't have the box. A normal 6-sided die rolled 100 times would have a nearly 22% chance of rolling 6 20 times or more. So without the box, there's no reason to view a die rolling 6 20 times as particularly interesting. If we assumed that this outcome was representative when it isn't, our probability estimation will get worse. In fact, if we had a normal die, any adjustments to our probability estimation from our default assumptions of 16.7% would make our probability estimation worse. Everything I talked about doing for the last 10 minutes or so would send us in the wrong direction. We can describe theories and hypotheses as having explanatory power and predictive power. Basically, our assessments of what a good job they do at explaining or predicting phenomena or events. We need explanatory power for why or how probabilities inherent to the event of rolling the die may differ from a normal die. The more satisfyingly we can say why or how probabilities may differ from purely random outcomes, the more justification we have in spending our time testing these outcomes and assuming that the outcomes reflect long-term predictive power. Now, I should say, sometimes you do find predictive power before explanatory power. Sometimes, after testing, results will be anomalous in a large and persistent way. Imagine rolling what you think is a normal die, but getting 9,000 sixes in 10,000 rolls. Even without an explanation for why this is happening, there is definitely reason to believe your next die roll has closer to a 90% chance of rolling a 6 than it does to a 16.7% chance. But we should still seek to build a credible explanation for why these results are happening. The more satisfying an explanation is, the more it should give us confidence that the results are reflective of long-term predictive power. Ideally, we are always pairing explanatory and predictive power. And predictive power is more useful with explanatory power. Coming up with an explanation could give clues as to when results may change, and can just help us be more sensitive to the greater context in general. For example, maybe the die has a magnetic face, and the 10,000 rolls were done on a magnetic surface. Now, I'd kind of hope someone would notice that rolling a die 10,000 times, but whatever. The point is, this explanation lets us know that these results would not continue if used in another environment. It basically clues us into another factor we need to consider in our probability estimation. So basically, the box gives a credible reason to believe the probabilities of the die rolling a 6 are worth investigating. It doesn't completely close every explanatory gap. It doesn't, for example, explain by what mechanism the die is weighted, but it does at least give some explanation for why the probability of rolling a 6 would differ from what we might otherwise expect. So here are what I think are the major takeaways of thinking through scenario 2. First, our probability estimates don't require absolute confidence in a single true probability inherent to an event. And second, we are best served by pairing explanatory power with predictive power. Now, I know I haven't really talked about trading explicitly at all yet, though I hope the connection between this material and trading is still evident. But let me throw in here the observation that so much so-called trading strategy that one finds in books and especially online does not satisfactorily pair explanatory power with predictive power. It's honestly rare to even see it attempted. And I think this is one aspect of why nearly all of it never really seems to work. Alright, I feel like this video is kind of a lot already, so I'm stopping part 1 here. It's reasonable to question the relevance of the scenarios I've covered in this video to trading because the dice in each scenario are stable in a way that market events may not be. But these scenarios lay important conceptual groundwork for the next part. So here's what to expect in part 2. More scenarios that, while not explicitly about trading, better resemble trading in some ways. More clip art! And shocking developments to the Kento's Precision Weighted Dice Company.